Okay, hello everybody. Now we will begin topic 5, the digital representation of units. We will discuss the challenges implied by the digital representation of units of measure. We have 4 excellent speakers for this session, Robert Hanisch from NIST and Stuart Chalk from the University of North Florida, representing CoData, Stephen Ray speaking about QDT, and Michael Trott from Wolfram. I'm Jim Fedchak from NIST. I will be the moderator. And Rodolfo Sousa, would you like to say something about yourself?
I am from the Metro, and I will control the chat and ask everybody to put your questions on the chat.
Okay, thank you. And so our speakers today for the first talk will be Robert Hanisch and Stuart Chalk. They will be talking about an approach to interoperability for units of measure. Robert Hanisch is the director of the Office of Data and Informatics from the Material Measurement Laboratory at the U.S. National Institute of Standards and Technology, NIST, which is my institution. His team provides data management and data sharing solutions for the organization and manages the NIST portfolio of standard reference data. He is a member of the Research Data Alliance Council and chairs the CoData Task Group, Digital Representation of Units of Measure. He earned his PhD in astronomy at the University of Maryland, studying extended radio emissions in clusters of galaxies. Stuart Chalk is a professor in the Department of Chemistry at the University of North Florida. Although trained as an analytical chemist, Stuart's interests are now in the areas of chemical informatics and data science. Stuart's research is focused on machine accessibility of physical property data, chemical terminology via the IUPAC Gold Book, automatic extraction and annotation of chemical property data from PDF files and scientific data models. So for the following talk, the topic will be recent developments with QDT, quantities, units, dimensions, and type. That will be Stephen Ray and again Stuart Chalk. Dr. Stephen Ray is an independent expert in the use of ontologies and formal representations to ensure unambiguous definitions of terms and relations, particularly for interoperability and standards in the smart electric grid, the Internet of Things, manufacturing, and medical devices. He has a 27-year track record of initiating and leading technical R&D projects related to information standards at the National Institute of Standards and Technology in the USA, followed by a decade as a distinguished research fellow at the Carnegie Mellon Institute. He's currently a CEO of QDT.org, a nonprofit founded to provide semantic specifications for the units of measure. And then the next talk will be units, scales, constants, physical quantities, and dimensions in the Wolfram language. That will be by Michael Trott. And Michael Trott studied physics at the Humboldt University of Berlin and received his PhD in theoretical solid-state physics at the Technical University of Ilmenau. He has been a member of the Wolfram research since 1994. In 1996, he wrote the first line of code for Wolfram Alpha and has worked for Wolfram Alpha since then. Today, he is the chief scientist for Wolfram Alpha, helping to realize the dream of making the world's knowledge of quantitative sciences easily accessible, especially physics, chemistry, and biology, and also putting mathematics in a form both computers and humans can understand, use, and extend. Outside of this, Michael is interested in the early history of the metric system and the Vienna circle. Okay, thank you.
Hello, I'm Robert Hanisch from the U.S. National Institute of Standards and Technology. And I'm here today with my colleague Stuart Chalk from the University of North Florida and talk about an approach to interoperability for units of measure. Units are ubiquitous and fundamental to all practices in science. Units have, until now, or until recently, really been for humans. We read about units in publications, and we see symbols and so forth, and everybody basically thinks that there is no problem, that we have solved the ways to represent units of measure. But in fact, when you're talking about computers and making units understandable semantically by computers, units are not solved. We need definite identification of units of measure for machines in order to facilitate interoperability of data. If you don't know the units and you can't properly compare them, then you really can't do metrology or other sciences properly. There are a number of drivers for improving interoperability of units of measure. For example, the United Nations Sustainable Development Goals require integration of data from very disparate resources, and those resources may have units represented in very different and incompatible ways. CODATA is initiating a decadal program, which is also emphasizing cross-domain grand challenges, where interoperability of units of measure will be essential. And this is a tenet that underlies the FAIR principles, findable, accessible, interoperable, and reusable data, where metadata needs to be sufficiently detailed such that units of measure are understandable by machines. The good news is that there are a number of well-established digital unit representations. We don't need another standard, but we do need to facilitate interoperability, and we need tools that can convert and find units and metadata describing rich data sets. There are several activities around this problem of representation of units of measure. There's a CODATA task group on the digital representation of units of measure, DRUM, of which I am the chair, and Stuart is a colleague of mine working on that task group. There's also CODATA engaging with the international scientific unions and the DRUM in order to solicit use cases and challenges. And in the social sciences, there's the Data Documentation Initiative Cross-Domain Integration Program that is also being done in collaboration with CODATA and the DRUM task group. The Research Data Alliance also has an interest group that is focusing on the UN Sustainable Development Goals. And so there are many groups now engaged in trying to rectify some of these challenges. I'll now ask Stuart to take over and talk about the current landscape for representing units of measure.
Thanks, Bob. The current digital unit representation landscape is quite varied, and as you can see here, there are a number of different specifications and/or implementations, kind of separated out into both encodings and ontologies. Now, these are just examples of these two categories, but what has happened is individual disciplines have basically decided they needed to formalize units within that discipline, and therefore they have created their own encodings. As far as ontologies are concerned, there are a number of ontologies around units, Qedt being probably the biggest one right now, and the presentation that comes next is going to go into Qedt in a little more detail. Now, in addition to these specifications and implementations, which are text-based and often used in databases, units are also represented within software and operating systems across different scripting languages, and also in document formatting standards. And so in terms of the different string representations of units, there are a number of variants. Next. You can see on this slide that I have aggregated a number of string representations of the unit, the mole, and kind of given you kind of like a picture of the variability that exists currently. clearly, it's important that these representations are used and understood, but the interoperability between these representations is very important, obviously, for making data interoperable in the grand sense. And so trying to develop a service to be able to identify and align these different encodings of units is an important priority. Next. In addition, there are just formatting strings that are variable for representing different units. This is meters cubed. And as you can see, there are a variety of different strings that represent that particular unit. And it would also be good if these text-based strings are able to be translated between the string representation and the appropriate unit that they represent. So we have to include those in any system that is developed. Next. Just quickly, a couple of very simple pain point examples. Here we have a slide showing data from different microscopy experiments, where, as you can see, not only are the units of measure not represented, not labeled in the present in the pictures, but also the number of digits used to represent the numeric value is certainly far beyond the number of significant digits. So clearly we need to make sure that the community does at least annotate units of measure wherever necessary. Next. In addition, this is an example of the representation of molar volume, the unit centimeter cubed per mole, in a PDF document, where, as you can see, there are a number of different representations. Some are good, some are at least the appropriate unit, but are not particularly well formatted, and some are actually clearly wrong. And so in terms of natural language processing applications for units, it's important that that publishers, in addition to authors of papers, make sure that unit representations are in some fashion standardized so that they can be made interoperable. Next. So there is a lot to understand about the extent of the digital unit representation landscape in the different ways in which units are implemented. We need to gather use cases to understand the scope of needs to support interoperability of these different unit representations. We also need to capture a significant number of pain points to identify additional solutions that are needed to solve those pain points. As part of ongoing efforts, we need to determine what tools and services, therefore, we need to support any and all entities that need to identify and align units of measure so that they can be made interoperable. And we want to reach out to different communities and disciplines to make sure we understand their needs, so they understand their needs and approaches to using digital units moving forward. Next. Thank you very much for your attention, and we're happy to answer questions in the discussion.
Thank you.
Hello, and thank you for the opportunity to present an update on the Qedt ontology at this Congress. My name is Steve Ray, and I'm the CEO of Qedt.org, which is a 501c3 public charity nonprofit incorporated here in the United States. So I'd like to start by just giving you a listing of some of the key features of the Qedt ontology. It is a set of modular graphs distributed both as OWL and shackle, the shapes constraint language, accompanied with a set of vocabularies of units, quantity kinds, dimension vectors, physical constants, systems of units, and systems of quantity kinds. For the linked data community, these are all fully resolvable URIs, all the vocabulary instances and quantity kinds, all the individuals, as well as the URIs for the graphs themselves. One thing that's somewhat unique about the Qedt ontology is we have a well-defined grammar for naming the unit URIs, which makes it somewhat easier, more predictable how to find a given unit of interest. for inclusion in your own application. All of these files are encoded as turtle RDF. And in addition to both the files, a set of static web pages to explore QEDT, we also offer a dynamic Edge browser. Edge is a product from Top Quadrant, which offers a dynamic viewing experience as well as Sparkle querying and a Sparkle endpoint. So finally, QEDT is licensed under a Creative Commons Attribution 4.0 license, which means it can be embedded inside commercial tools for sale without any need for any royalties of any kind. And I refer you to the QEDT.org website for specifics. So here's the essence of the ontology itself. We have the notion of a quantity, which is a contextual concept. Say the height of a building would be a quantity, which has associated with it then a numerical value, say 15.2, a unit, say meters, a quantity kind, which is in this case length, as well as a dimension, which points back to the dimension vectors inherent in any system of units and quantity kinds, such as SI, where you have, of course, the 7 base dimensions, as well as 7 base units. So that's the essential pattern. Here's an example of a very simple use of QEDT, which is just a single quantity which has a numerical value, 72 you see in the example, an associated unit, and the unit is then in turn associated with a quantity kind. This is the very simplest way. You can see some code there, how it would be written. There are more complex patterns. For example, if you wanted to store multiple pairs of values and different units, you can also do that in the QEDT ontology. So everything, as I mentioned, is defined in terms of these dimension vectors. And the reason that's so important is it then allows automated unit conversion, dimensional analysis, these kinds of things, commensurate units that can be checked either in Sparkle itself or Shackle or your own application, of course. Here are some statistics for the current population of units and quantity control available for distribution. I'd like to also mention that QEDT does contain cross-references to many other international standards so that you could, for example, use the UCUM literal representation for a unit to find the QEDT equivalent, and from there navigate to the quantity kind and do any computations you might care to do. So we are trying to have many such connections there. Here's a partial view of the web browser interface. You can see human readability. We have LaTeX descriptions for many of our units and quantity kinds. We cross-reference the symbols, and you can see on the right there the other standards that have an equivalent to a particular unit. I'd like to spend a few minutes discussing this issue here, which is that QEDT has served multiple distinct communities. And I think this is important for anyone trying to standardize on how to represent units. Initially, and probably earliest, was the linked data community, which is more interested in up-to-date, the latest version of something, but fully resolvable URIs. So they can simply make reference to a URI and they receive back a snippet of code which describes what that unit or quantity kind is all about. Now that's quite different from the industrial use community, who are more interested in careful management of version control. They want to download these graphs and have them remain fixed in their own application until such time as they are ready to make a careful migration to a newer version. And we use a GitHub release mechanism for this, such that you can use it as a downloaded artifact rather than online through the linked data paradigm. We offer both the choice of the OWL representation of the schemas or Shackle, a shapes constraint language. OWL has been around, of course, much longer. The Shackle representation allows a more expressive capture of some constraints and behavior, which we take advantage of, for example, in that Edge browser for dynamically inferring properties which might otherwise have been explicitly stated in the vocabularies for the linked data community. So we want to make sure it's available for use with or without the need of using a reasoner in conjunction with it. So you can take your pick in that sense. But this is important to think about in terms of what should be standardized. Do you want to have a core from which one can infer other properties, or do you want to go ahead and explicitly assert all of these other inferences for simple downloading? It's not an easy question to answer. Finally, here are some links to the QEDT homepage, and it has actually cross-references to our GitHub repository, documentation, many other resources. So in the interest of time, I'm not going to go into all the other things you can do with QEDT, but I would like to stress that we are an open source project. We depend upon community involvement for contributions, error checking, new units, domain expertise, and all. And I would invite you to consider participating in that way. So with that, I will stop and will be available for any questions you might have. Thank you.
Good afternoon, everybody. Thank you for coming to my talk. I want to talk about unit quantities, physical quantities, and physical constants in the Wolfram language today. First question, why do we care about units in the technical computing systems? And the answer is pretty simple, because many real-life computations that modeling the real world do contain dimensional parameters. This means one needs a semantic computational encoding of observables and results of observations, meaning measurement results. That's why in 2012, in the version 9 of the Wolfram language, we introduced the function quantity with arguments magnitude and unit and a bunch of related functions that work with it. We had already started a couple of years earlier working with unit when we worked on Wolfram Alpha. That was released in 2009 and now powers personal assistants like Siri and Alexa. The reason is that a good fraction of quantitative queries that people ask are either direct unit conversions or queries that need units to even formulate a question, or an even larger number of queries that have a quantitative result that turns out to be a quantity with dimensional answer. So before going into the actual quantity framework, I want to quickly discuss the syntax of the Wolfram language so that some of the examples become easier to understand. We only discuss the interactive in-out paradigm, not the remote computation of a batch session. So here we have an input, and we can evaluate it, and we see here in and out. We will frequently see in-out with a little bit grayed out with a bullet, like this one. And the reason is this is from the last time I had this mathematical notebook open. And if I evaluate it, then it will instantiate it to the current in-out in this session. I will not evaluate everything for timing reasons. Wolfram language functions are typically uppercase and internally capitalized. So contour plot, quantity magnitude. Square brackets are used for function application, like sinus, log base b, comma x. Curly braces are used for ranges, domains, iterators. And the percent sign refers to the last result. So for instance, if we evaluate this input, we can refer to it and numericalize it with any precision. The arbitrary precision arithmetic becomes very handy when we deal with quantities, because quantities frequently are only measured to a finite precision. Now with respect to the computational representation of things, other than mathematical objects, one needs dates, molecules, quantities, an object of the real world to really compute with them. So here's a quantity 3 meter. I can compute this. The result is nicely formatted, easy to read, has a tooltip. I can take the result, add something, I can convert it to another unit. Here's the current time instance, and I can say what is now minus this, and it shows that the difference between two time instances is, of course, a time difference. And then we have this concept of entities in the Wolfram language. Entities are all kinds of things of the real world, like persons, elements, music recording, dog breeds, food, and so on. Here's, for instance, the entity New York City. I evaluate it, and it becomes this yellow box. And I can ask questions about this, like how many people live there. And we see it's a quantity with the unit people. Now a quick overview over the main quantity-related functions. So we have already seen there's quantity and a bunch of other built-in functions to represent and work with quantities, physical quantities, and physical constants. They all have a compact and editable output formatting, which is very convenient, easy to read. They work smoothly together with visualization function, numeric and symbolic computation functions. And units, meaning the second argument of quantity, can be classical units like meters, seconds, but they can also be physical constants like the speed of light. And the default output, metric or imperial, is customary, depends on your GeoIP. That's a quick overview. So in the center of it are quantities like 3 centimeters, 5 meters. They have units inside. Then units have physical dimensions like length, mass. Then there are quantity variables. They can be potentially be named like a voltage V. Then we need, of course, uncertainty computations if we work with units. And we need physical constants that define units. And then many things like geo, dates and times. So here's a list of the most important functions. Quantity we have already seen. Quantity variable is something like the quantity variable V representing an electric potential. Unit convert, unit simplify, also pretty self-explanatory. Unit dimensions, mass, length, time, temperature. And there are around 2,000 other functions. The Wolfram language has currently around 6,000 symbols, and this is a lot, but you don't need all of them all the time. But adding a couple thousand more units to remember would make it not easier. That's why we have a very convenient way to type them in. For instance, you have a quantity, and then it already proposes the most commonly typed units at this point. There are still at this level many to choose from. Or you can use control equal, which allows any natural language input. That's the functionality we use on Wolfram Alpha to understand natural language. For instance, here the product of Boltzmann constant times 300 dK Kelvin. The result is fully computational, so you can convert it, say, to electron volts. If you have a large number of such natural language expressions, you can use the function interpreter to process them programmatically. For instance, here's 2 times 198 kilometers, and so on and so on. And this gives a euro amount by the end of the day. Couple words about the scope and breadth of the data about units and related functionality that we have. We have around 5,400 different units, obviously all SI units, including prefixes, but we have also many thousands of historic and international units. Here are some examples, like here are some GGS units, genetics, some from astronomy, some historical ones. And we have also collected more than 12,000 compound units. Of course, you can form any compound units that you ever wanted, but this doesn't mean people use it in practice in a certain field. Knowing what kind of compound units actually occur is very important for making appropriate choices for simplifying compound units. Physical quantities, we have around 2,700 of them. They work very similar, also have a tooltip. And here's a list of them with their standard name, their canonical units, and their dimensions. Physical constants, we have around 320 of them. Obviously, all codata ones, the latest and the historical codata values. We supplemented this with constants from astronomy, cosmology, particle physics, speed of light, Planck constant, Avogadro constant, Boltzmann constant. We also have ones that are related, say, to Earth flattenings, ratios of mass-sun. And you see, whenever possible, we have exact values of them, which is not possible with the new SI. Otherwise, we very carefully keep track of what's the current precision that the latest codata values allow. So I want to show some quick examples. Here's a sum of 3 lengths, 12.7 meters, 3.603 kilometers, and a small factor multiplied by 5 light years. We can evaluate it. We can convert it, say, to miles. Here's a ratio of 3 joules divided by watts. Note that we don't simplify automatically the units, but we keep it as joules over watts. But of course, you can simplify. And here's a mixed radix quantity, which very nicely formats. Mixed radix obviously is important for feet, inches, hours, minutes, seconds, and so on. Some example for physical constant. Here's a Planck constant. I evaluated, converted to SI base, which is an exact number, an exact fraction. Here is the Josephson constant, also exact. I can, of course, numericalize it to any precision. And here's the famous Eddington-Weinberg relation. I can just evaluate it. It stays symbolic. I can convert it, and to the relatively low precision, we know the Hubble constant. These two numbers indeed agree, and future physics will probably show the deeper meaning of this relation. Now, physical constant. Here's a quantity variable for an electric potential called V. Here are its dimensions: current, length, mass, and time. Not unexpected, the canonical unit is volts. Here's the Lagrangian of a classical pendulum. Note that these are not just symbols, they're all physical quantities. This means we know the dimension of this object. And we can get, say, the Lagrange equations, and then make a small angle approximation to get a classical formula for a pendulum that we learn in school. Some small applications, how to work with units. We have 1200 plus formulas from physics. Here's, for instance, the Planck radiation law with the wavelength as the independent variable and the dependent one is spectral radiance. We can compute explicit values by using concrete wavelengths and temperatures. Here's a nice example, shows nicely how everything works together. Take F equal ma and have a given force, a given mass, and that's the acceleration expressed as second derivative of time. But note that it's not just a symbol, it's actually quantity variables. This means we can supplement this one with initial conditions, then solve. Now we have the solution of differential equation, and we can plug in a time to get an explicit result for the position. Okay, some data applications. Assume you want to do some more complicated searches. You want all elements with a density between 9.1 and 10.1 gram per cubic centimeter. So just to formulate a question, you need obviously units. And we look at all elements, we get all metals with this density, and bismuth probably be the most known one among exotic metals. We can look, for instance, what are the carbon spectral lines that are in the visible range. We can visualize this. A thermodynamic computation, what is the viscosity of air at a certain pressure and temperature, what's the current sidereal time in Paris, and the result is a mixed radix quantity in hours of right ascension, minutes, and seconds. Some applications for units and quantities in daily life calculations. These are entities of type cookie that have chocolate chips added. We have around 100 different of them. What kind of nutritional values? Or given a 14-year-old male, what's its height within 1 sigma? Human growth data provides us with this. Socioeconomic data are a very interesting case because they have some units that are typically slightly outside of the SI, like persons or counting units. So here, beer per capita production over the last 50 years, we get back a time series. And the elements of the time series themselves are quantities of dimension kilogram per person and year. Some applications from geography. Here are some aerial images of the northernmost and southernmost points of the Machine, the Lumber expedition. We can calculate, say, the distance between these 2 points to millimeter precision. Here are the geogravity data, and we see a relatively large horizontal component, which is conjectured to be one of the reasons why our meter is 0.4 millimeters off. Computational chemistry and genomics. Here's a Coffin molecule. We can represent it as a symbolic object, and as such, it has, of course, properties. For instance, we can calculate its molar mass, its energy, and the force field minimization, and we can calculate its principal moments of inertia. Here, let's retrieve the mean male height and male weight for 375 dog breeds, pretty big dogs and pretty small dogs. And we see in a log-log plot, they lie pretty much on a line. And we know from general allometric scaling ideas that we would have a relation that the weight is proportional to height to the alpha with an exponent between 2 and 3. And we can quickly carry out the optimal fit to this nonlinear model, not just of the log, but the original one, and get 2.4 as the exponential scaling parameter for dogs. Let's look at a slightly more esoteric example. Pokemons. We know that humans' weight is log normal distributed. Human height is normal distributed. What about Pokemon weights? There was a paper in Journal of Physical Society 2019 investigated. If we make a plot on a logarithmic axis, we see in a first approximation a Gaussian curve. So Pokemons are indeed having a log normal weight distribution, and we can say compute the optimal distribution for the parameters of the log normal distribution. And if we look at them, they really span an enormous amount of scales from 90 grams to nearly a ton. So a couple of words on extension and some potential issues. Let's take 22 euros per hour. We can convert this, for instance, in dollars per minute, where we have to do actually 2 conversions, the simple ones being hours to minute, the more complicated one, the one being euros and US dollars, where we use the current exchange rate. But what about euro from 2006? To indicate that as an old euro, we have the concept of a dated unit where we can say from when it is, and then we convert, say, a euro from 2006 to a euro to 2016, and we see around a 15% change due to inflation. Dimension of angles. Everybody who follows metrology knows that there's a discussion about the topic. Do angles have dimensions, and is it better to have them or is it better not to have them? In our system, we decided to consider them to be having dimensions. This means something like an angular velocity has dimensions angle over time. Counting units is another interesting subject that you need for practical applications, even if the SI is not very specific what we should do with them. Like you have 5 slices of bagels, 8 cloves of garlic, 200,000 web hits. To deal with them in an optimal manner, we have many of them as built-in ones, and obviously there are always more things you can count than one can have. Nearly every countable noun is something you could count. We also have the possibility for users to extend the system with more counting units. Non-multiplicative units, meaning additive and logarithmic ones. There is some ambiguity, for instance, in the degree Celsius. SB 811 from NIST says that the degree Celsius can be considered either as a difference or as a scale. Here we have the degree Celsius and here we have degree Celsius difference. So we carefully differentiate the two because if you convert them to kelvins, one of them is more or less, of course, the same, where the other one is, of course, a much bigger number. Earthquakes are complicated because they are logarithmic. They are complicated for the system as well as for users. Not only being logarithmic, they are having some other complications due to slightly fuzzy conversions. Some representation details. Normally in a symbolic system, if you have x over x, you evaluate it to 1. But what about 2.8 micrometers by meters? Do we want to convert this to 2.8 times 10 to the minus 6 as a unitless quantity? And we decided not to do this by default because 2.8 micrometers over meters is really something else than 2.8 microseconds over seconds. If you wanted, you can force the system to make them dimensionless. Just a couple of words about physical constants. Here are some random ones. And we have one very nice property, equivalent forms, which gives you various versions to write a certain physical constant, in this case, the Bohr radius. It is nice because once you have a sufficient amount of these equations, you can actually do algebraic computations with them. For instance, figuring out what's the influence of an error in one of the physical constants. Here we take this list of representations and plug in the latest code data value, and it matters which order you do all of this because the resulting precision is slightly different. Some application of working with dimensions. Dimension analysis still very popular and in use. Here's a very classic example, Taylor's estimation of the explosion power of the Trinity bomb. So what you have at your disposal, you have the mass density of air, you have the radius of the ball visible, and you have the time after which it was photographed. And this uniquely gives you this quantity that you can form of dimension energy. You can plug in the values, and you get around 26 kilotons, which is pretty much the right result. Another application of the use of dimensions is the de-dimensionalization of equations. For instance, you have a time-independent harmonic oscillator Schrödinger equation, and you want to get a form that is free of any units and dimensions. So we have this function non-dimensionalization transform with old variables, new variables. Here's the result. And we also get the explicit instructions what to do with the dependent and independent variables and the parameter to get to a pure equation with no dimensions. Okay, as said, measurement results always have uncertainty, so it's important to do computations properly by taking uncertainty into account. Here's a very simple example. Take one with pure numbers, no units and quantities involved. Of course, we could do it with units and quantities. Say we have 2.4 plus minus 0.1. The function in Wolfram language to represent uncertainty is around. So we have this, and then we can carry out proper Gumstyle arithmetic that takes all correlations, potentially vector valued, into account with correlation matrices, and we get this result. Of course, you could also just substitute it, but then because we missed any correlation, we get a much larger uncertainty. Being able to do it properly with uncertainty is, of course, important for more and more domains, like the Kepler mission that looks for the exoplanets. They report very nice error bounds and everything, so we can detect them and visualize them and see where a potential future habitat for humans might be. Sometimes one doesn't just want to do an uncertainty calculation, but one has to be a little bit more precise because one needs very high moments or the actual distribution. We can work with built-in distributions. Here's a so-called quantity distribution, where we have voltages that are distributed according to a Wigner semicircle, a uniform distribution for the current, and then we can use just Ohm's law to calculate what is the expected value of the resistance, and we can also calculate the actual distribution. And here are some visualizations. So the half circle for the voltage, the uniform for the current, and the resistance is more complicated. Here's a closed form for the distribution. Okay, and I think it brings me to the end of my talk. So quick summary. There is a very detailed documentation of all of the 2000 unit and quantity related functions that we have in the Wolfram language. If you go to the Wolfram language documentation, here's a snapshot of the website. Then for some more advanced application examples for the version 12 of the Wolfram language that came out 2 years ago, we prepared a larger number of examples, what you can do with all the functionality available. And last, I put a version of this talk with some more examples in the cloud. You can just go to this address and try all these examples yourself, can modify them, rerun them, and you don't need an account to do this. And if you have any questions for me or the units team at Wolfram, don't hesitate to email me, and I will answer as fast as I can. Thank you very much for your attention.
Okay, thank you. Hopefully everybody can hear me.
Mm-hmm.
So those are very excellent talks, and we have some questions. And I'm getting some feedback here, so I'm gonna try to. Yeah, I'm gonna try to mute myself. I'm gonna try to mute myself.
Well,
That was bad. Okay. Okay, that's better. Hopefully everybody can hear me now, and
yes.
I'm not getting the feedback that I was getting before. Okay, so we have some questions, and so let me see if I can read some of these questions for you guys. And this will be the discussion part, so people can still enter in some questions, and hopefully we can get to all of them. So the first question is, would it be possible to expand QDT to include labels, symbols, and definitions in other languages? And Stephen, that's for you.
Can you hear me okay? Yep. Okay, absolutely. In fact, what we do, and we've already got US English and International English as two language tags in our entities. As an open source project, we would love to have anyone come in and augment our vocabularies with, French, Spanish, Chinese language tags for all of the labels. As far as symbols are concerned, we do cross-reference symbols to the other standards or the commonly used symbols. But yeah, absolutely no reason why we could not expand the vocabularies for all things. And definitions, of course, yes.
Okay, great, thank you. So we have another question for Michael Trott. Does Wolfram Alpha have any plan in the works to make their amazing code and techniques available for greater interoperability with other systems such as QDT, UCUM, etc., to better fulfill the goals of these seminars' FAIR principles?
Can't hear you.
Oh, we can't hear Michael.
Okay.
We heard you for about 1 second and then you cut off. No.
Okay, so why don't we see if we can fix Michael's audio, and we'll go into another question, and we'll come back to that if we can. So another question are we considering you as a use case the use of biosensors that consider the integration of physical chemical and biological quantities? So are we considering as a use case the use of biosensors that consider the integration of physical, chemical, or biological quantities? And I guess this could really be, I guess it could be a question for just about any of the speakers. Do we have a volunteer to answer this question?
I can take that one. I think in a general sense, we're looking for any and all use cases. I mean, the whole point about this is that the SI is used across many different disciplines in many different ways. And as a consequence, we have to support or try and support any and all use cases for the use of SI units. And as I mentioned in the presentation, that includes scripting languages and software that has built-in systems to be able to deal with units of measure. So I think any use case you can think up is appropriate in this space.
Okay. Does anybody else have any elaboration on that?
No, I agree with Stuart. I think no reason
I would
not.
just add that we are more than happy to accept additional use cases. Participants have sent in about 10 or 12 of them to me, and I'm happy to have more.
That's great. So Michael, can you be able to speak now?
I hope it works now. Okay, good. I'm glad. I don't know what it was.
Okay.
Of course, we want the work and the collecting of data that we have done over the years to be used as much as possible, and we try to implement as many standards and units and versions, how units be written, what values they have for all the ones they deviate from each other as much as possible. So right now already Wolfram Alpha does have an API. So you could use the API if you wanted to programmatically processing. Say you have a set of a text file with units, you can send it to Wolfram Alpha and get a machine readable version back. You could do something similar with the cloud version of the Wolfram language, where you could build interfaces. There's a function called form function, where you can have, say, natural language input or computable input and get it back programmatically, and you can deploy this and use on your own website wherever you want. And if you have any other suggestion what we should do for more interoperability, let me know and we can discuss.
Okay, thank you. So let's see, we have another question. So it says, can you do a quick mapping that tells us what kind of tools can make our systems interoperable in terms of FAIR? So I assume that this could be answerable by everybody, but perhaps Steve or Michael, this would be a good question for one of you.
Okay, I'll jump in. I mean, I think, yeah, we try very hard to be abiding by the FAIR principles already, which is why we take pains to make all of our URIs dereferenceable so that they convert, they return something with a query over the internet. So and the fact that we're open source and Creative Commons licensed, which makes it reusable. So FAIR principles are very central to the work we're doing already. I don't know about tools to make them more fair. I think we're kind of trying to be fair already.
Okay.
I guess I could add to that too, that the work that we're doing between NIST and Stuart, and maybe Stuart can chime in here about a web service that he is working on that does automated conversions and representations of units of measure in several different representation systems. That's something we want to make available through APIs. such that one can dynamically interpret and convert units from one data set into those in another representation.
And I would just follow that by saying, you know, that's a kind of a dedicated web service, but I understand through one of my colleagues, Simon Cox, that I know he's been working with QDT to help get interoperability increased. I know that they have UCOM codes, as Steve has mentioned, in a lot of the units, and obviously there are other representations of units also embedded into QDT. So in a sense, we've got a start of tools. I think this workshop is all about, in a sense, trying to get the community to tell us the scope of tools that are needed in this space, because just because we can think up things that we think are appropriate doesn't mean to say, well, we'll think of everything. And so if either of those tools do not kind of like serve your need, and we need to know what kinds of tools you need to be able to support what you're doing.
Okay, well, thank you. We have another question. Could you please explain the distinction between quantity and quantity kind? I'm thinking about hierarchical change, such as extensive quantity, energy, thermal energy, Gibbs free energy, which are all the normed terms. For example, in the ISO 80,000, which are quantities and which are quantities and which are kinds. And I assume that this would probably be a good question for either Bob or Stuart.
Actually, I think this
Steve
might be using, it's a QDT terminology, the quantities and
Okay.
quantity kinds. And very simply, quantities have values, quantity kinds don't. So a quantity kind like the ones he lists, you can't, it's not meaningful to ask, what is energy? What's the value of energy? Well, that doesn't make any sense until you give it a context. That's what a quantity is. So what's the, you know, what's the height of my house is something that has a value. What is height doesn't have a value. So that's the easiest way to distinguish. One is contextual, one is context free. As far as the hierarchical chains, we use the Scoss-Otter hierarchy to relate those things he lists in the questions. One would be broader than the other in a Scoss sense. That's a simple knowledge system. So that's how we deal with quantity kinds. That's all I got to say.
Okay, thanks. So we have a question from Daniel. He says, to Steve, you mentioned resolvable URIs. How do you deal with the potential need for persistent resolving to the URIs?
Yeah, we subscribe to the idea of persistent URIs. These are designed to be persistent. We register the prefixes we use for QEDT with prefix.cc. I know there are various governance bodies to register persistent URIs. I'm probably ignorant of some of the nuances of that, but we want these URIs to be persistent.
Okay. I don't think there's any more questions in the chat. If anybody has any more, please send them in now. And we have a few more minutes here, so I will ask a question, and this could actually be answered by anybody, and I think it has relevance probably to everybody. So I have a question like, there are some units that have dependencies, and I think that's been referred to in some of the talks. As, for example, the one that I'm familiar with in the work that I've done in the past is flow. Some people express it in units of throughput, and it can be easily expressed in SI units like Pascal liters per second. The problem is that it needs to be, when it's expressed that way, it needs to be specified at what temperature. So a lot of times people will say, you know, STP, standard temperature and pressure. And the problem is there's really no standard for that. So some people will call it 0 Celsius. That's what we typically would do at NIST. But other people might call it 25 degrees C or 23 degrees C or something like this. And you see these conventions. For something that doesn't really have a standard, how would we handle that as a unit? Does anybody care to comment on that?
I'll jump in there. I don't think in of itself it's really a unit issue. It's
Right.
something else that the expert group has been discussing, and as part of the grand plan here is the idea that we work towards analysis ready data, which means we represent the numeric value, the unit, the quantity, but then package that in some fashion. That means there are also the contextually important additional conditions that are the basis for, or put the context around that particular piece of data. So, in a sense, this is part, units are just part of a much larger, in a sense, structure to correctly contextualize the meaning of a piece of data so that we can actually do something useful with it.
Right. Physical constants are a great example, right? A physical constant, the speed of light is not any speed of light, it's the speed of light in a vacuum, away from gravitational influence and things. So there's physical constants have to deal with this context issue in their definitions. Sure. I'm sure Michael's confronted that.
Yeah, we have exactly the same problem. Like by the end of the day, is you want a slightly bigger object. You want the quantity, 5 meters, then you want what you said earlier, it's a height. So you want the PQ for the quantity associated. If possible, a little bit something more specific than the height, as you say, the height of your house. And then you want it potentially supplemented with the current pressure conditions and temperatures at which it was taken. And this whole thing you want to roll up in one data bundle that you process. Yeah.
Right.
Thank you.
Like it's especially important we're working on, say, material data where it really matters. Like for many pure physics, it's relatively clear what you measure. But if you have material data and you have some young modulus of some material, it really matters at which temperature was this, how was the material pre-processed. So it's important to keep this all together.
Good. Thank you. So another question came in, 2 more. One is there's more an issue of defining quantity that was a comment on the answer. Okay, it says that's more of an issue of defining the quantity rather than the unit. A question is, Steve, for those of us who are just starting out on the digitization path, could you tell us what the role of an ontology is in the framework of interoperability?
Wow. Okay. Well, this is definitely something I've spent my career on. So this is my wheelhouse. Interoperability, I believe, is all about sharing of data, putting it simply, but it's contextual data, it's sharing of understanding of data, which is why I believe that ontologies are so much of an advance over just syntactic interoperability. So you want to make sure the receiving party of a piece of data understands what your intent was when you send a piece of data. There are so many examples in the literature and in the media of misunderstandings as the cause of interoperability failures, whether it's NASA sending SI units when their contractor was expecting British units and losing a lander in Mars, or whether it's something ambiguous like a shipping date. And what does a shipping date mean for a manufacturer shipping something? Is it when it was received at a loading dock, or when was it, actually shipped from the factory? These kind of misunderstandings cause great concern, in contracts and payments and things like this. So the whole point of an ontology is to drill down the meaning, the intended meaning of terms as much as possible. And during my time at NIST, this is what I was proselytizing as the next generation of all normative standards could be in the form of an ontology, a formal semantic, rather than natural language text. Natural language is beautiful and artistic, but it's ambiguous. We need to formalize definitions of terms if we want interoperability. Sorry, a bit of a soapbox there.
Thanks, Steve. Okay. All right, thanks. So this concludes our session. I thank you all the speakers. This was very educational for me, and I'm sure for all the audience as well. It's really been great, and we had some great questions too. So this concludes this topic session for today.
Okay.
I'm live. Okay. So is the slide up? Okay. Okay, so here we have the slide, the schedule for the remaining workshop. So we have completed day 3, and tomorrow we will continue on with day 4, and then this slide shows the schedule here. So hopefully we will see you tomorrow.